space and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. A total eclipse. The brilliant sun suddenly obliterated by the black disk of the moon.
You can see this eyeball looking down at you.
Both breathtaking and frightening, eclipses warn us of powerful solar storms that may fulfill an ancient prophecy of chaos on Earth in 2012.
People would freak out. We wouldn't have refrigeration, we wouldn't have lights.
Eclipses of distant stars are now revealing new planets, even other Earths.
Some of them just popped right out at us.
The search covers the entire universe, but it begins here on Earth as the sun hides its face in total eclipse. It's a spectacle in the sky that has enthralled human beings for thousands of years. A total eclipse of the sun. Few people who see one will ever forget it.
Personally witnessing a total solar eclipse in the flesh is an amazing, awe-inspiring, tremendously moving experience. I've never experienced anything quite like it.
Some, like astronomer Glenn Schneider, are part of a subculture of globe-hopping eclipse chasers who will go anywhere, anytime to see an eclipse.
It grips you because the sky has gone dark. Not as dark as midnight, but like a very deep twilight. And you can see this eyeball looking down at you. The black disk where the sun was is the silhouette of the moon. It's an experience that you can't believe it was only a minute or 2 minutes. It seems to have lasted a lifetime and also just an instant.
This compelling event is a launching pad for cosmic exploration, solving a string of mysteries that have puzzled mankind for ages. What makes the sun disappear without warning? When does it happen? How can we predict it? Can we make it happen ourselves? Once understood, we find that each eclipse reveals something new about the universe. Even now, we're finding our newest eclipses around distant stars, revealing extrasolar planets, some perhaps twins to the Earth, with the potential for life. The story begins with the mystery of our own eclipses. A sun suddenly vanishing in broad daylight. Visible since before recorded history, the ancients regarded eclipses with wonder and fear.
The ancient people didn't understand physically what was going on during a solar eclipse. They would see a progressively bigger bite being taken out of the sun, as though some gods or dragons were eating the sun, mad at those people. So the people would beat pots and pans and yell and scream and sacrifice virgins and all sorts of things to appease the gods and scare the dragons away. And you know what? It worked every time.
Through thousands of years, patiently watching the movements of the sun and moon in the sky, ancient astronomers realized eclipses happen when the moon passed directly in front of the sun. In time, scholars studied the patterns of eclipses, long enough to predict them. The Babylonians discovered what's called the Saros cycle, more than 22 centuries ago.
The Saros cycle is a cycle of eclipses that repeat every 223 months, roughly every 18 years, and they're very similar to one another.
The Greeks were aware of the Babylonian discovery. As we've learned from the remarkable Antikythera mechanism, an ancient device found on a shipwreck under the Mediterranean Sea in 1901.
The Antikythera mechanism was first thought to be some sort of a clock and then some sort of celestial timer. It was a very complex mechanism with many gears and layers and planes.
Archaeologists have been intrigued by the Antikythera mechanism ever since it was found. Decades ago, they understood it was a mechanical computer for calculating movements of the planets, phases of the moon, and other astronomical phenomena. But the latest discovery astounded them. In 2008, using 3D X-rays and CT scans, they found that the Babylonian Saros cycle was built into the device.
In two of the back plates of the mechanism was inscribed a spiral-like figure that had divisions that, when you added them up, corresponded to the months in a Saros cycle. The only reason to have the Saros built into the mechanism was if it was an eclipse predictor as well.
A total eclipse of the sun can be seen somewhere on Earth an average of once every 16 months. Today, predicting them is a very exact science.
The next total solar eclipse to be visible from the United States will be on August 21st, 2017.
But modern astronomers can do much better than supplying the date for an eclipse. An eclipse map shows the exact path along which people can see the 2017 total eclipse. And the timing is down to the second. It will reach totality at 10:17 plus 18 seconds a.m. in Salem, Oregon, at 1:15:55 seconds p.m. in St. Louis, Missouri, and 2:41:55 seconds in Columbia, South Carolina. It will cross the country in 1 hour, 31 minutes, and 1.6 seconds, along a path averaging 66 miles wide. With information so exact, anyone who wants to see it will be able to.
People will have an opportunity to get to the path of totality from all over the United States. It's an opportunity that everybody should really try to take because they're few and far between.
Apart from the spectacular visible picture, the blocked sun also gives viewers the chills, in a literal sense. During a total solar eclipse, the temperature can drop as much as 35 degrees. That, of course, is nothing compared to the temperatures in outer space, where all the action is taking place. How cold can the universe get? That's what Carlo of Boulder, Colorado wanted to ask the universe. So he emailed us. What is the current temperature of the universe? And why is it so cold?
Carlo, that's a really cool question, if you'll pardon my pun. Here near the sun, we feel warm. But in outer space, the temperature of the universe is only 3 degrees above absolute zero. It's really cold. It's that cold because the universe can be thought of as an expanding gas, and it's been expanding and cooling for 14 billion years.
The reason total eclipses are few and far between is the result of a delicate astronomical interplay. It depends on a moon that's an average of about 240,000 miles away and 1/4 the diameter of the Earth.
To demonstrate just how difficult it is to get two objects to align just right to create an eclipse, I'm going to use this ping pong ball representing the Earth and this very small marble representing the moon. This is so small that I have to hold it in tweezers for you to be able to see. Now, the Earth and the moon are located about this far apart in space, and it makes it very difficult for them to align just right with the sun to create an eclipse, as I'm going to demonstrate. It's very difficult to get these to align just right for an eclipse to occur. But once I do, I can see a fuzzy shadow on this ping pong ball. that looks very much like the beautiful photographs of solar eclipses from space.
The large fuzzy part of the shadow is called the penumbra. If you're standing in the penumbra during an eclipse, the sun is not completely covered, and you see a partial eclipse. The small, dark central part of the shadow is called the umbra. If you're standing in it, the sun is completely covered, and you see the total eclipse. Because of the moon's motion in its orbit, the umbra moves across the Earth, tracing a clear line called the path of totality, the only place where a true total eclipse is visible.
The width of the umbra is typically under 100 miles, so you really have to position yourself carefully in order to see a totally eclipsed sun. And seeing a 97 or 98% eclipse is nowhere near seeing a 100% eclipsed sun. You've got to be in the path of totality.
There is much more to the eclipse phenomenon than just the sun and the moon. The story reaches across the universe, because eclipses do happen everywhere.
An eclipse occurs whenever one object passes between us and another object, cutting off its light.
Virtually all other planets with moons will also have solar eclipses, whether they occur here in our own solar system or around other stars across the entire expanse of space. But what can this eye candy of the cosmos teach us about the universe? How is it possible that a simple eclipse on the Earth can prove that the bizarre distortions of space and time predicted by Albert Einstein are essentially correct? Our search for total eclipses begins with what we witness from the Earth. In space, satellites use eclipses of our sun to watch for disasters like the fabled solar storms of 2012. But farther out in the cosmos, our explorations reveal that there are eclipses everywhere. Many of them keys to unlocking secrets of the universe. In the solar system, the only planets without eclipses are Mercury and Venus, because they have no moons.
Currently, there's about 170 known moons orbiting planets in our solar system. Now, that number keeps on growing. Saturn and Jupiter each have at least 60 known moons, but as we get better and better data, additional small moons are being found. So I think there are hundreds of moons in the solar system.
In most cases, the moons are too small to block the full disk of the sun. Mars is a good example. Taken from the surface by the Opportunity rover, these NASA photos show the Martian moon Phobos as it moves across the sun. It turns out that the eclipses we see here on Earth are like no others.
In order to get the kind of eclipse that we have here on Earth, where it's a total eclipse, but the moon just fits over the sun so that you can see the corona and how dramatic that is, requires a remarkable alignment of size and distance.
It amounts to a coincidence of cosmic proportions. The sun is about 400 times bigger than the moon. But the sun also happens to be about 400 times farther away from the Earth than the moon. What that means is that both the sun and the moon appear to be almost exactly the same size in the sky. Their sizes in the sky are crucial for eclipses.
Suppose this ball represents the sun and the small red ball represents the moon. To get a total solar eclipse, they have to be perfectly lined up with each other and with the Earth. Now, in this case, the moon is too far from the Earth, so it looks too small to fully cover the sun's disk. But as I bring the moon closer to the Earth, the moon looks bigger and bigger. Now, eventually, the moon is close enough to the Earth that it perfectly covers the sun's disk. That's a perfect total solar eclipse.
What are the chances that this remarkable alignment would happen on a planet at just the time in its history when an intelligent species has evolved to witness and wonder about the results.
It's interesting to speculate whether any other intelligent beings in our Milky Way galaxy experience such beautiful, perfect total solar eclipses.
It's really quite possible that we may be the only intelligent species in the entire universe that has this kind of alignment because it is so specific.
And while ancient humans once dreaded solar eclipses for hiding the sun, another kind of eclipse helped to answer what was once a fundamental question. Is the Earth flat or is it round? The puzzle was solved when the Earth and Moon went into a celestial role reversal. The result was a lunar eclipse.
By watching the shadow of the Earth pass across the Moon, the ancients were able to actually see that the shadow was curved. Therefore, they were able to infer that since the shadow is curved, the Earth itself must also be spherical.
The curvature is prominent when only part of the Earth's shadow passes across the Moon. But when the Moon is entirely shadowed by the Earth, the lunar eclipse is total.
If we lost electricity for 3 months or more, the effects, especially on a country like ours that depends on electricity so much, would be devastating. You can only imagine what it would be like. People would freak out, really. I mean, we wouldn't have refrigeration, we wouldn't have lights.
Without the artificial eclipses in our solar satellites, we would have no idea that such a threat even existed. According to recent estimates, full recovery could take 4 to 10 years. Millions of people could die due to shortages of food, clean water, and pharmaceuticals. Projected damage may be as much as $1 to $2 trillion, comparable to 20 Hurricane Katrinas. A super CME struck the Earth 150 years ago, but scientists disagree on when the next one could come.
The likelihood of that happening in our lifetime is probably not that good, but we just don't know. We don't have enough data.
The most powerful coronal mass ejections that could cause widespread damage over all of Earth probably occur only about once every millennium or so. Nevertheless, having a huge calamity every few thousand years is really a big deal.
Our best protection may be in the artificial eclipses aboard spacecraft monitoring the sun for CMEs. If improved warning systems are put into place, we may have enough time to shut down the electric grid to prevent it from burning out, dodging the deadly bullet, otherwise aimed straight for us. A coronal mass ejection may be the most spectacular phenomenon uncovered by eclipse science, but the universe is full of other eclipses, each one teaching us something else about the cosmos. Even a short hop into space, no farther than the Moon, turns the tables on us as the Earth becomes the celestial body to eclipse the sun.
Think about how important that Apollo 12 image was, where they turned the camera back towards the Earth and you could see the Earth eclipsing the sun. Those images from Apollo were really epoch-making for humanity. It gave us our first real sense of the Earth as being an object floating in space.
Farther out, the Cassini space probe looks at Saturn, virtually black, surrounded by backlit rings as it blocks out the disk of the sun nearly 1 billion miles away. A very different view of our own moon eclipsing the sun comes from the Stereo B spacecraft. From deep space, the moon appears much smaller, and it crosses the sun's disk in what's called a transit. This kind of eclipse may be pivotal in answering our questions about who else may be out there in the universe.
What makes transits so important is it's one of our ways of actually discovering what are called extrasolar planets, planets orbiting other stars.
The tantalizing possibility is tempered by the daunting problem of actually making it work. Finding a planet transiting in front of its star is like seeing a flea crawling across an auto's headlight. But science is rising to the challenge. And new space telescopes, trained on the tiny eclipses that uncover planets around distant stars, are about to strike gold. After centuries of wondering, the discovery of another Earth in the depths of space is suddenly within reach. If the search for eclipses starts with the most spectacular examples here on Earth, turning our view out into space reveals other eclipses, not only in the solar system, but far beyond, where they're key to one of astronomy's hottest pursuits, the hunt for extrasolar planets.
A very important kind of eclipse right now is the eclipse that occurs when an extrasolar planet, a planet orbiting another star, passes in front of the parent star. It takes a very sensitive telescope to detect that slight dimming. The most famous telescope project right now is the Kepler Space Telescope that is out there in space looking at over 100,000 sun-like stars and watching over a period of years for the transits of actually Earth-like, Earth-sized planets going in front of those stars.
It'd be great if we could find planets orbiting other stars by simply pointing a telescope up into the sky and taking a picture of one. But that's really tough. One of the reasons that that's really tough is because the stars are about 10 million to 10 billion times brighter than the planets that orbit them. And I can demonstrate that really easily with this searchlight. When I turn it on, you see that I become completely lost in the glare of this light, just as a planet is lost in the glare of the star that it orbits. Kepler's job is to measure the brightnesses of stars, just like we can do with this light meter and our simulated star, the searchlight.
This is how eclipses figure into the mission. The light meter's needle dips when something passes in front of the searchlight, creating an eclipse. Kepler does the same thing, but is so sensitive it can detect a dip of 20 parts per million.
Kepler is capable of detecting an Earth-sized planet around a sun-like star in the habitable zone. So a real Earth-Sun analog, that's what Kepler's capable of doing, and it's the first mission that's capable of doing exactly that.
Kepler is trained on an area of the galaxy containing about 150,000 stars. And it monitors every one of them constantly, measuring each star's brightness every 30 minutes, hoping to detect those minute eclipses caused by planets around some of them. Just a small fraction of them will be in the right position for us to see their planetary transits.
Most of the stars in the sky that have planetary systems don't undergo transits. It's only if we have a lucky chance alignment where the orbital plane of the planet is along our line of sight or contains our line of sight to the Earth that we can actually see when the planet goes in front of the star and dims out some of the star's light.
The very distant combination of light and shadow produces for each transit a telltale light curve showing the dip in brightness as the planet crosses in front of its sun. Kepler produced results after only a few months on the job.
We looked at our very first light curves. We could see transits immediately. I mean, some of them just popped right out at us. The spacecraft was performing flawlessly. The data was beautiful. Right out the gate, we were reaching the precision levels very close to what we expected at the beginning.
In January 2010, the Kepler team announced the discovery of the mission's first 5 planets. 4 are gas giants like Jupiter. The 5th the size of Neptune. Kepler saw their transits many times in its first weeks of searching. It means they orbit their stars in a matter of days, eclipsing their stars each time.
These things are closer to their parent star, about 10 times closer to their parent star than Mercury is to our sun. And Mercury's the closest planet to our sun.
But one of Kepler's ultimate goals is to find Earth-like planets around sun-like stars. And that takes longer, since they will orbit on timescales like our own, once a year.
An Earth-like planet around a sun-like star is going to produce a dimming of 1 part per 10,000. So it's a very tiny signal.
If it's in the habitable zone, that signal, the transit, is going to last 12 hours and would repeat once every year, not once every 3 days. So you have to stare, you have to have stability, you stare for a whole year and you wait for an event that happens and lasts 12 hours and is very, very tiny, 1 part per 10,000.
When Kepler spots the right kind of light curve, large telescopes on the ground follow up. They take additional measurements to be sure the eclipses are caused by planets. It means weeding through a lot of data.
As of June 2010, we had approximately 700 planet candidates.
The confirmation work now being done by ground telescopes is painfully slow and will continue for months and years to come. As the process continues, Kepler's planet list is expected to grow to dozens soon, and later hundreds. Measuring Kepler's success rate is guesswork, but as many as 50% or more of its candidates may turn out to be actual planets. Kepler will search for tiny eclipses for as long as 6 years, accumulating a census of planets in our galaxy more complete than any compiled so far.
Kepler's going to determine if Earth-like planets are common or rare. And the answer either way is going to be very interesting. If it turns out that they're rare, that speaks to how special we are in the galaxy. However, we have reason to believe that they're going to be frequent. I think we're all kind of closet optimists that they're going to be very common, but we don't know. We don't have the answer yet.
In this, the discovery of Earth-like planets around other stars, eclipses will be the tools making it possible. Far removed from the sensory thrill that the chasers seek in witnessing the moon block out our sun, eclipses in deep space may lead us to the ultimate knowledge of our place in the cosmos. By blocking out the light from some of the most luminous objects in creation, it is as if we are screening out the deafening noise and are now hearing only the secret and revealing whispers of the universe. In the beginning, there was darkness, and then bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. It's the apocalyptic finale of our galactic neighborhood.
Probably the most dramatic event in the entire history of the solar system.
We've now uncovered sizzling clues about our home star's violent demise. And the outcome doesn't look good for planet Earth.
You could experience both death by fire and also death by ice.
New cutting-edge science traces the real horrors awaiting our planet as our sun unleashes its final fury.
The kiss of death for everything.
Our sun. It's bathed us with light and energy for over 4.5 billion years. But like all things in the cosmos, our nurturing star will eventually die. And Earth could literally melt into the sunset.
When the sun gets 100 times brighter than it is now, the entire surface of the Earth will be incinerated. All the rock that composes the continents will melt and run into seas of molten lava. The Earth will be uninhabitable.
The death of our sun will have a profound effect on our cosmic world. We rely on our home star, located in the center of our solar system. Over 1 million Earths could easily fit inside this gargantuan ball of bubbling gas, with core temperatures reaching 30 million degrees Fahrenheit. The sun is approximately 93 million miles away, so Earth is not too hot or too cold. It's the perfect distance to sustain oceans of liquid water and abundant life.
We're incredibly dependent on the sun's energy for our survival. First and foremost, plants utilize solar energy in photosynthesis so that they can grow. And then we use plants for food, and so do other animals, and we eat those other animals. We also use the fossil fuels from partially decayed plants. Winds are also generated by the sun's heat. We're using solar energy everywhere.
All this life-giving heat and light comes from the sun's core. A colossal nuclear reactor comprised of 3/4 hydrogen and the rest mostly helium with traces of heavier elements. Here, hydrogen nuclei combine to form helium nuclei. This process, called fusion, gives off radiant energy.
This car is like a newly formed star, like the sun. When a star like the sun is born, it's born with a full tank of gas. So if I fill this tank with gas, that's like the hydrogen coming together gravitationally, forming a hot, dense core. That gas will later burn. In the case of a star, hydrogen will fuse to form helium, giving the star energy. Just as in the case of the gas burning in the car, that'll give the car energy with which to move.
Like an automobile, the sun will eventually run out of fuel. And Earth will be without this crucial power source.
The rate at which it's fusing hydrogen into helium, it will someday simply run out of hydrogen in its core. We can see other similar stars that were born much earlier than the sun, and they're now dying.
To track our sun's dark future, we travel back in time to its beginning. These exotic clouds of gas and dust are called nebulas. They consist of the remnants of dying stars. But upon closer observation, they're actually stellar nurseries, where stars like our sun were born.
About 4.5 billion years ago in our galaxy, a giant cloud of gas and dust gradually was pulled together by gravity. And as gravity caused that cloud to collapse, a lot of energy was released, it heated up, and finally in the center, nuclear reactions started, changing hydrogen into helium, and a new star was born.
The remaining stellar material swirled around the newborn sun. It collided and coalesced, eventually sculpting the 8 planets in our solar system, including Earth.
When that happened, a stellar wind turned on and cleared out all the extra material, leaving the planets that we have today and additional bodies, some of which collided or merged with the other planets.
Among the billions of points of light in the universe, our sun is an average star. There are stars 100 times its mass. And contrary to its appearance, the true color of the sun differs from what we see when it rises and sets.
The sun is actually a white star, not a yellow star. It's white, like this car. Now, it's true that the peak of its spectrum is sort of in the yellow region, but it also emits some blue light and green light and orange and red, and all those colors together are perceived by our retina and our brain as the color white.
Our sun has a lot in common with humans. When it was young, it was extremely active and often unpredictable.
What we found was really very surprising. We found that stars like the sun, when they're very young, are rotating much, much faster than today. If you can imagine something as big as the sun just whipping around in one day or even less, that was a very different kind of sun. It was having all kinds of eruptions that blasted particles through space that hit the Earth.
Right now, our sun is middle-aged and has settled into a quieter, regular schedule. But it's still generating a lot of energy.
The sun right now is about 4.5 billion years old. It's slightly under half of its total anticipated lifetime. So it's kind of like this car with a little bit more than half of its tank still full. The sun now is burning fuel, that is, fusing hydrogen to helium, at a steady but ferocious rate. It's like a 90 billion megaton bomb going off every second. It's just an incredible amount of power.
On Earth, we're actually only receiving about 1/2 billionth of the energy that's being produced at the sun. Now, on a daily basis, that's enough energy to power about 29 million billion 100-watt light bulbs for 1 hour. The amount of energy being generated in the interior of the sun is just enormous.
Our sun will continue to churn out energy over its entire lifetime, which is estimated to be around 12 billion years. In the 1990s, scientists confirmed its age and when it will die by measuring its brightness and original mass, as well as analyzing its sound waves.
Light doesn't penetrate the sun, it's opaque. It sounds strange because light comes from the sun, but light can't pass through it. So until recently, there was no way to probe the deep interior of the sun. There's a science now called helioseismology that uses sound waves to actually probe the interior structure of the sun. And so we have a very good knowledge of what the interior structure of the star looks like. And that's allowed us to constrain and confirm the models of the sun's age and its evolution.
Strangely, our sun is now 30% brighter than it was at birth. As it ages, it will gradually grow even brighter and more powerful.
Our climate is very sensitive to the energy from the sun. So if you're worried about global warming, you worry about what humans are doing to the atmosphere, but you also need to know what the sun is doing to the atmosphere. The most recent estimate says that maybe 20% of all the warming that's happening, the global warming, is due to the sun.
In 1 billion years, our star's luminosity will be 10% greater. And temperatures on our planet will be 100 degrees hotter.
The moisture in the air is very good at trapping infrared radiation or heat. And so it's sort of like putting a blanket on the Earth. Now here's the bad part. As the Earth warms up, the oceans evaporate even more, we trap more heat, and so the Earth warms up more. And when the Earth warms up more, again we trap even more heat, and the effect can run away. It's what we call the greenhouse effect.
With this surge of heat due to the runaway greenhouse effect, life on Earth will be in peril. Whole societies will need to retreat to underground shelters during the day, then emerge at night when the temperature cools down. But as the thermometer continues to climb, there eventually will be nowhere to run or hide.
We know how that story ends. It's called the planet Venus. If you think about it, Venus is only about 30% closer to the sun than the Earth is, but it's way, way, way hotter, 800 degrees. We don't quite have the technology that would allow us to survive on the surface of Venus, but we could imagine what would be required, insulating yourself from the heat. So it would be a challenge.
In 3 billion years, our sun's brightness will increase 40%. By this time, oceans will have boiled off. Earth will have become a global desert.
The sun will have used up about 3/4 of the hydrogen in its core, fused to helium. Like this car is 3/4 empty. By this time, the sun will be brighter than it is now and bigger, so Earth will be hotter. It won't be a nice place to live at that time.
And the solar nightmare is far from over. As the sun nears its 10 billionth birthday and beyond, the most drastic changes will occur. If human-type civilizations are still around, what will be the options for survival when our sun eventually fills the entire horizon? It's a foregone conclusion. When the sun is about 10 billion years old, it will run out of hydrogen fuel in its core. It's the beginning of the end for our star, and it won't die peacefully. As for Earth, global warming or other cataclysms could snuff out every living thing in a mere 1 billion years. But if human descendants somehow manage to survive until then, they could face a living hell.
When the sun burns through all of its hydrogen at its core, it will eventually start contracting on itself because it's no longer burning through the hydrogen, fusing it together, creating this radiation pressure outwards to balance the gravitational pull inwards.
While hydrogen fusion will stop in the core, it will continue to fuse at a faster rate in the shell surrounding the core. The extra energy will expand the outer layers of the sun.
That'll mean that the sun will grow much more powerful, much more luminous, because the hydrogen shell will be fusing while the core is contracting at a greater rate than it normally would. All the pressure from the energy generated in this hydrogen fusing shell will cause the outer parts of the sun to expand, making it into a red giant.
A red giant is a star that has exhausted the primary reservoir of hydrogen fuel at its core, leaving behind a buildup of the heavier, denser helium. An average-sized star like our sun will spend the final 2 billion years of its life as a red giant.
We call it a red giant because as this expansion happens, the surface area gets so great that it actually cools off. And in terms of temperature, stars that are cooler appear redder.
During the initial red giant phase, catastrophic changes will occur. Our sun will swell to 20 to 30 times its original size and become 100 times more luminous. As our red giant sun expands, it will continue to vigorously fuse hydrogen in the shell surrounding the inactive helium core, thus producing more helium in the core.
As that happens, the core of the sun collapses further and gets hotter, and the sun gradually expands over the course of a couple of billion years. Eventually, the core of the sun is hot enough to ignite the helium. You get what's called a helium flash. It's like the stellar equivalent of the big woof when you light a gas barbecue.
The ignited helium will be hot enough to undergo fusion, now creating carbon and oxygen in the core. The dying sun will be resuscitated with this new but temporary form of energy.
I'm stuck here in the desert and I've run out of gas. But you know, I have a spare gallon here in the trunk. And if I pour this gas into the gas tank, that'll allow the car to keep going for a while longer. This is kind of similar to the sun. During the red giant stage, it's going to run out of hydrogen as fuel, but it'll have helium that can briefly, for a few tens of millions of years, fuse to carbon and oxygen, providing a new source of energy that'll keep the sun going for a while longer.
At the end of the initial red giant phase, the dying sun will enter this stable helium-burning phase. It'll become hotter, yet somewhat smaller, but this is merely a lull before the storm. This is because the sun's transition to a red giant actually comes in 2 phases. During the second phase, the helium will be exhausted in the core, which will now consist of carbon and oxygen. The core will again start to contract and heat up. But helium will still exist in the shell, and it will continue to fuse, forming more carbon and oxygen in the contracting core. And all of this will be surrounded by the hydrogen shell that's still fusing to helium.
When the sun becomes a red giant, it will expand out, and the first thing it'll do is engulf the planet Mercury and eventually incinerate it, evaporate it, eat it up. Then it'll expand out to Venus. After the helium changing into carbon uses up all of its energy, Then the core begins to shrink a second time, the outer part expands a second time, and it's not very stable.
During the second red giant phase, the wild contraction and expansion will make our sun pulsate like a slow beating heart. The pulsations can occur every few hundred or thousand years. And with each pulsation, planetary pandemonium will ensue.
Mercury and Venus are doomed. They'll be engulfed by the red giant. However, there's been some debate in the scientific literature as to whether the Earth would actually be engulfed or not. The sun will be large enough to engulf the Earth.
Earth's future is uncertain because it lies on the borderline between being engulfed and surviving. But astronomers now have one possible sneak preview of our planet's ultimate fate. The Infrared Optical Telescope Array has captured close-up photos of a Death Star, Chi Cygni, which is approximately 50 light-years from Earth.
Chi Cygni is near the end of its red giant stage, when it's grown really big. And in those last few million years of existence, it starts pulsating. It actually pulsates every 400 years or so, getting bigger and brighter and smaller and fainter.
If the massively bloated star Chi Cygni were our sun, it would have consumed every planet out to Mars. Earth and all its wondrous forms of life would have been melded with the materials inside the dying star.
We obviously haven't been around long enough and will not be in our lifetimes to understand exactly what's going to happen when the sun dies. So we need to look to other stars in order to see how that might work.
Observations of other Death Stars have offered a startling glimpse at our own sun's long-term prognosis and what's in store for the rest of the solar system. Earth could be catapulted into the fiery abyss. However, recent research indicates that with the right set of cosmic conditions, a shockingly different fate may await our fragile planet. All things must end. In about 5 billion years, our motherly sun will stop nurturing its planetary offspring. As it begins an agonizing death march, it will expand 100-fold and devour the planets Mercury and then Venus. Near the end of its second red giant phase, the sun will contract and expand several times. With each pulsation, our dying star will become dangerously close to swallowing Earth. However, with the right set of circumstances, our planet could be spared.
There's a phenomenon called the solar wind that's continuously blowing, lifting material from the outer layers of the sun's atmosphere out into interstellar space. When the sun begins to expand into the red giant phase, the outer layers of its atmosphere are even more loosely bound than they are now. And so the solar wind will be much more prominent.
The data indicate that if the solar wind blows off about 30% of the sun's mass, its gravitational pull will weaken enough to allow Earth to move sufficiently outward.
If the sun loses some of its mass, its gravity gets weaker, and the Earth's orbit is going to get bigger. So if we're lucky, our orbit will expand out enough that it will miss the expanding sun, and we won't get incinerated.
But Earth won't be completely removed from harm's way. While the sun might lose mass, it could also have a tidal interaction with our planet. And this could have sizzling consequences.
There are at least two competing effects. Although as the sun ages, it's losing mass, and that means that Earth's orbit gradually drifts away from the sun, it's also true that Earth, being pretty close to the surface of the sun, will raise a tide, a bulge of gas on the sun. And a gravitational interaction between that bulge and the Earth will actually slow down the Earth in its orbit, causing the Earth to gradually spiral in.
So maybe the loss of mass will move us out enough to be safe, but maybe the tidal forces will spiral us in enough that we'll be engulfed and the Earth will be incinerated. And if you come back in 5 or 6 billion years, you'll know which one wins out.
Earth just might get lucky. An international team of astronomers discovered a planet outside our solar system that survived the death of its home star. The exoplanet is at least 3 times as massive as Jupiter and orbits the star, dubbed 391 Pegasi, which is about the same mass as our Sun.
Some exoplanets clearly do survive through the red giant stage. For example, 391 Pegasi is a star that has an exoplanet around it, a planet orbiting it, and that planet is still there. Now, it might have a rocky Earth-like core and perhaps even an iron central region, but we think it's mostly gaseous and liquid.
391 Pegasi and its gas giant planet have a similar orbital distance from each other as Earth does from our Sun, which is about 90 million miles. Astronomers think the exoplanet survived because its death star lost mass, which reduced its gravitational pull on the planet just enough so that it drifted slightly outward.
The planet around 391 Pegasi is likely to be one of these planets that have sort of walked the knife edge between spiraling outwards and being dragged in by tides. You would not expect to find a lot of planets in that particular range of distances. You would expect them to either be completely swallowed or have them be much further out. And so it requires a somewhat delicate balance of the two competing forces to actually enable a planet to survive at that sort of location.
So there's one case in which the planet survived. The bad news is that in this solar system, the planet is really big, larger than Jupiter. And so it probably has a better chance of surviving than a small planet like the Earth would.
It appears that stellar winds and thermal pulsations produced by 391 Pegasi pulled atmospheric material from the outer layers of the exoplanet and hurled it into space. However, the gas giant planet survived because it could afford to lose a lot of mass.
We can speculate that it may have lost one or more Earth masses of material. And of course, if the Earth lost that much material, it wouldn't be here. Certainly, a Jupiter-sized planet, a gas giant, isn't inhabitable by people, but it's still intriguing that if the Sun went to the red giant phase, it's possible that Jupiter would survive.
The continued existence of the gas giant planet orbiting 391 Pegasi doesn't provide conclusive evidence one way or the other whether Earth will survive the death of our Sun. But one thing seems certain. Long before our Sun becomes a red giant, our planet will no longer be hospitable for Earth-type life. Any future civilizations will need to relocate, and billions of years before the impending inferno.
About 1 billion years from now, if viewers were around, I'd recommend that you move to Mars. Mars, instead of being too cool like it is now, would probably have a somewhat more favorable temperature. If there is water underground in Mars, and we don't really know one way or the other for certain yet, maybe you could use some of that water and you might have a comfortable retirement on the planet Mars.
But the move to Mars wouldn't be simple. The red planet would be warmer than it is today, but it would still be missing a few of life's necessities.
You have to create an atmosphere. You have to have pretty high pressures in order to have molten water on the surface. You need to somehow generate oxygen. Just because a planet or a moon is in the habitable zone doesn't mean that it's already habitable.
If you were a strategic planner, you would encourage the growth of plant life on Mars 1 billion years in the future. You would generate oxygen, and you'd make that planet more hospitable for us. Perhaps a little egotistically, we call that terraforming, that we could form another planet in the shape of Terra, or the Earth. I hope we're here to do that.
Even if an advanced society manages to colonize Mars, this new home will be temporary. The Sun will continue to become brighter and bigger, pushing the habitable zone even farther out. During the red giant phase, Earthlings will have to move again, perhaps to the water-rich moons of Jupiter or Saturn. But with every new location, there will be more obstacles.
Near the end of the Sun's red giant stage, it will rapidly be growing much brighter and much bigger. So we'll need to move to the new habitable zone much more frequently. Another problem with moving to a new planet or a moon is that it would be very difficult and expensive to move all humans. So whom do you choose? Just some elite subset of society? That would create great problems.
Instead of abandoning Earth before the sun becomes a red giant, another alternative might be to actually move the entire planet. This may sound like science fiction, but technologies are already being considered that might rescue Earth from the solar apocalypse. Predictions about our sun's demise are widely accepted. In about 5 billion years, our star will begin a long, violent death. As it mushrooms into a red giant, it will vaporize planets Mercury, Venus, and most likely, Earth. If human-type civilizations still exist, they will have already relocated to the outer solar system. And they may have even hauled Earth away with them. The challenge will be finding the right cosmic moving van.
We might gradually move the Earth to a new habitable zone by, for example, taking an asteroid and bringing it into an orbit so that it comes reasonably close to the Earth every once in a while and gives it a gravitational tug outward.
Right now, scientists are running computer simulations to test the feasibility of actually moving Earth using manned or drone rockets.
In order to do that, we would either have to use solar sails, perhaps, to direct this asteroid into the correct place, or maybe a fusion-powered rocket. In 1 billion years, we may have other technologies that, are much easier, and who knows what we can do by then.
Researchers have determined that an asteroid would need to be rounded up every 6,000 years to keep nudging our planet outward as our sun grows in brightness.
If it does that very gradually, very steadily, but over millions of years, then we will gradually drift out, keeping pace with the drifting habitable zone.
Even if Earth could be reorbited beyond the danger zone, its future remains bleak. Near the end of the second red giant phase, the unstable pulsations of our sun will subside because much of its outer atmosphere will be ejecting away. However, this means its energy will be rapidly depleting.
There won't be as much mass, as much gravity pushing down on the thin helium layer and compressing it, and it won't be as sensitive to the temperature. At this stage, the sun will actually become smaller and hotter and bluer, not red and big and extended.
And so the nuclear reaction rates are going down. So eventually, when the star has lost enough mass, those reaction rates basically die away. So the star, in this case the sun, will eventually run out of fuel and it will start to shrink.
Unlike other stars, our dying sun will not go out with a bang when it runs out of fuel. Some Death Stars actually produce a supernova explosion, a burst of radiation that can temporarily outshine an entire galaxy. But why won't our sun have a spectacular fireworks display upon its death? That's what one viewer wanted too. Ask the universe. So Leroy G. from Newport, Rhode Island texted us, why won't our sun go supernova when it dies?
Leroy, I'm sure glad the sun won't explode as a supernova. There's 2 reasons. First, the sun isn't massive enough to explode on its own. Stars have to be 8 or 10 times the mass of the sun to explode on their own. And second, the sun doesn't have a companion star from which it could steal material, grow in mass, and eventually become unstable and explode.
At the last stage of our sun's life, its outer atmosphere, a glowing sphere of gas called a planetary nebula, will have drifted away. All that will remain of our once powerful star will be a glowing white-hot cinder called a white dwarf.
It'll be about the size of the Earth at that point, and it'll have about half of its mass remaining. That object still has as much thermal energy as the entire sun did, but it's very small and doesn't radiate it very effectively.
White dwarfs are small, but extremely dense. Imagine our white dwarf sun as small as the Earth, but with the same mass as a whole star.
fact, if you were to take a chunk of white dwarf material the same size as the cell phone, it would weigh approximately the same as an elephant. So it's very dense material, although this white dwarf size is very small relative to the sun as we know it today.
As a white dwarf, our sun will slip into retirement, using up its life savings of thermal energy for billions, even trillions of years.
When it has become a white dwarf, it'll be like a car that's coasting. It's run out of gas, but it's still moving because it has energy of motion that's propelling it forward. It's not generating any new energy by burning fuel. It'll be radiating away the stored energy in its hot interior, energy that it had generated through nuclear reactions when it was young and vibrant. So it's like a car that's just going along without any fuel until finally, eventually, very slowly, it comes to a halt.
Anything left in the solar system after that transition to the white dwarf stage would just gradually cool off. It would remain in orbit around the white dwarf. The orbital decay times are extremely long, and it would just stay there as a quiet, cold, orbiting body forever.
Our white dwarf sun will become progressively cooler and dimmer. Since it's no longer generating energy, everything in the solar system will begin to freeze. As the sun's vital signs continue to dim, what will be the forecast for Earth? In its death throes, our aging sun will become insufferably hot as a red giant, and then unbearably cold as a white dwarf. This could be the kiss of death for planet Earth as it moves from the frying pan and into the frost.
By the time the sun becomes a white dwarf, we can imagine that temperatures on Earth, depending on where it is in its orbit, would drop significantly fairly rapidly because the white dwarf is no longer producing energy through fusion. So it's not producing this energy to heat the Earth.
We'll be fried to a crisp if we remain where we are during the red giant stage. But in a similar vein, we will go into a deep freeze if we remain where we are when the sun becomes a white dwarf. Nevertheless, there will be some pockets where life could continue to survive. For example, in the liquid parts deep in the oceans, it could survive.
At the outset, humans could theoretically live in submarines near hot hydrothermal vents while they dredge up the geothermal energy from deep within the Earth's core. But after 1 million years, the oceans would completely freeze, and life would inevitably perish.
After the sun becomes a white dwarf, it's just going to cool and cool. It's very much like a pot on the stove. Once you turn off the burner, there's no more source of energy, and so it just gradually gets cooler and cooler and cooler. If the Earth manages to survive until the sun is only a white dwarf star, it will hardly be getting any energy at all. I can say with absolute certainty that if you stick around long enough, you could experience both death by fire and also death by ice.
Without energy from our sun, all remaining life in our solar system will disappear. However, this disaster could be preempted by accomplishing what so far has been impossible to do: actually duplicating the sun's hydrogen fusion right here on Earth. Science has already been able to manufacture nuclear fission, which involves the splitting of atoms into lighter, smaller nuclei. This is the power that drives our nuclear power plants and ignites nuclear weapons. But nuclear fusion, which occurs in the core of the sun, requires putting nuclei together to form a larger, heavier nucleus. And so far, this process has not been achieved here on Earth.
The problem with recreating the sun's conditions is essentially getting materials to the densities and temperatures that you have in the center of the sun. The sun has its gravity to drive the pressures and densities up so it can get these high reactions. On Earth, we don't have the luxury of using the sun's gravity, so we have to find other ways to try and compress the material and generate the kinds of densities that you see.
At the Lawrence Livermore National Laboratory in Northern California, scientists are taking on the challenge by attempting to create a miniature man-made star. The experiment involves aiming the world's largest laser, the size of 3 football fields, at a BB-sized target filled with hydrogen fuel.
In an inertial confinement experiment like the one at Lawrence Livermore, you start with a small pellet, maybe a ½ inch across, the core of which is made of a solid material containing lots of hydrogen to undergo fusion, the outside of which has layers of different material that are engineered to produce a shock wave that will drive in and compress that core as much as possible.
The colossal laser will split into 192 separate beams that will strike the pellet housed inside a capsule. When the fuel pellet's shell is struck by these high-energy X-rays, it should implode and then ultimately produce nuclear fusion in its core.
If we had controlled, affordable nuclear fusion, it would change everything. Many things about our lives would change, but most importantly, we wouldn't need the sun anymore. We could produce energy, heat, light on demand. We could live anywhere in the cosmos with a supply of hydrogen and make our own energy. We could fly to other planets very quickly, in days instead of years. You can extract all the water you need from practically any material that contains hydrogen and oxygen. If there isn't enough oxygen around, you could make some.
Generating reliable nuclear fusion could ultimately save Earth and all forms of life by eliminating our dependence on the sun. Yet the sun's own fate is forever sealed. As a white dwarf, it will become dimmer and cooler. The star that once provided energy to an entire solar system will eventually fade from sight.
When the sun eventually cools off so much, you won't even be able to see it with your eyes. And so that's why some people call it a black dwarf or a dark star. It'll just be invisible, sitting there in space nearly forever.
Our solar system cannot dodge its date with doom in 5 billion years. But the death of one planetary system can spark the birth of another. Our sun's nebula will eventually blend together with other stellar material and spawn the next generation of stars. And one might even nurture another vibrant planet like Earth.